Good afternoon. My name is Steve Ferguson, and we're pleased to welcome you to the Washington Labs Academy webinar series. We hope you'll find the next hour or so useful and informative. We've developed these series to deal with the technical and administrative issues that our customers face on a day-to-day basis. We recognize that engineering challenges can be complex and we're looking for ways to support the technology industry. Before we begin, I would like to go over a few housekeeping details. First, I hope you can see the title slide it's on. This is episode 3 of the Bruce 6-Fact series, PCB Power Distribution and Optimization. First, we'd like to realize that the recording of the attendee sound is muted for the better quality audio to prevent noise from interfering with the speaker as we go through the activity. A recording is underway for this event and will be made available to all the people that signed in, or in future things, the recording can be purchased to continue activities. Please feel welcome to contact us. You may choose a full screen view to enhance your viewing. You'll have to select this with your Webex tools that are available. Select full screen for the larger presentation view. By all means, we'd love to hear from you. During the event, please contact us using the chat or the Q&A functions to ask questions or make comments. And we will answer these towards the end of the presentation. We will not interrupt the speaker. So please contact us. You can contact us here at Washington Laboratories through academy@wll.com or the phone number 301-216-1500. Just ask for an Academy representative and they'll put you into the right place. Or you can contact Bruce Archambault directly, bruce@brucearch.com. Don't hesitate. I'm sure he enjoys hearing from people with questions on his presentations. I'd like to introduce our speaker. Dr. Bruce Archambault is an IBM Distinguished Engineer, Emeritus at IBM Research Triangle Park, and an adjunct professor at Missouri University, Rolla, Missouri. He received his BSEE degree from the University of New Hampshire in 1977, his MSEE degree from Northwestern in 1981, and his PhD from the University of New Hampshire in 1997. His doctoral research was in the area of computation and electromagnetics applied to real-world EMC problems. He has held positions at Digital Equipment Corporation and Seth Corporation, supporting product design and EM analysis. In 1997, he joined IBM in Raleigh, North Carolina, where he is the lead EMC engineer responsible for EMC tool development and use on a variety of products. Bruce has authored or co-authored a number of papers in computational electromagnetics, mostly applied to real-world EMC applications. He's currently a member of the board of directors for the IEEE EMC Society. He is the author of the book PCB Design for Real-World EMI Control, and the lead author of the book titled EMI EMC Computation Modeling Handbook. He has lectured at the University of Oxford for the past 13 years. Let me welcome Bruce to the presentation. I will hand him control.
Thanks, Steve.
And welcome.
Thanks. Let me share my screen here. Well, welcome everyone.
It is visible.
Okay, good. Thank you. Welcome everyone, and thanks for taking the time to attend this seminar. We're going to talk about power integrity, or really printed circuit board decoupling capacitor design today. And I find that throughout the industry of printed circuit board design, people are fairly confused about how to do the decoupling design properly. There's a lot of myths out there. There's a lot of conflicting information. Some people will tell you that you need to use a variety of different value capacitors. Others will tell you, no, just one value capacitor is what you should use. Some will tell you it doesn't matter whether you put the capacitors near the IC or not. Others will tell you it's very important to put it near the IC. And so we get all these conflicting things out there. And today what we're going to try to do is look behind all the myths and just understand some of the fundamental physics and see what the best way to do this design is based on physics rather than just opinions. So the bottom line is that inductance is going to dominate the performance of the decoupling capacitors. And so then we might say, well, okay, we think we know what inductance means, but the current path from the decoupling capacitor into the IC is fairly complex. And so, you know, we can start saying what parts of the inductance are the important ones and when are they important? Under some circumstances, they may not be important at all. And then we'll talk about the effect of the capacitance value and the number of capacitors and density of capacitors and so forth. And we'll end up with a case study where we can kind of demonstrate some of these things on a real board. So first of all, we'll start this with basically a circuit board like this, and this is just an example circuit board that I pulled out of a real design. We had an IC region here, and we had some decoupling capacitors and so forth, and then we can look at what the impedance is that the IC power pins would see, and depending on how many capacitors are actually populated on the board, we would get curves that look like this down here in the lower left. But what we really want to do is convert this fairly complex layout here, and then the stack up, as you can see in the upper right, which is fairly complex. I want to convert that to a relatively simple circuit, and we can do that pretty straightforwardly. And so first of all, we look at the little part of the curve down here, and that's a capacitor. That's the capacitors, the planes as well as the decoupling capacitors. And so if we go onto the circuit here, we can see that we have the decoupling capacitors highlighted on different locations, and then that represents the capacitors on the actual stack up. And we also include the planes here. In this case here, the power and ground plane pair is in the middle of the stack up, and that's included here in the circuit as well. And so we've represented all the parts of capacitance here with this equivalent circuit. And then we can start looking at the inductances. And so this mid-range inductance here is actually a combination of inductances. The LIC is the inductance that the IC pins see as it comes down through the vias, however many vias there are, down to the power and ground plane pair. And that's represented by the inductance of the vias here that have been shown. And then we have some inductance associated with the current traveling along the planes here. And you can see highlighted in the stack up, and that's also included in the circuit. And then finally, we start looking at the individual capacitors, and we have inductances associated with the capacitors, and whether they're on top or bottom, we have all those inductances here. And so now we have all those parts there to make up this equivalent inductance that's seen by the LIC, the L planes, and the decoupling capacitors, and of course there's mutual inductance associated with these things as well. And then finally, at the high frequencies, we can look at this high frequency inductance, and that's associated only with the IC vias. And so from the IC power pin point of view, it looks down through these vias, and you can see that's represented here as it was a moment ago. But that's all that's the only thing that's happening at high frequencies. Okay, so now that we've broken that up, let's think about how decoupling capacitors actually work. So a lot of times we look at impedance plots like I showed you a moment ago, but actually if you only look at the magnitude of the impedance, we're missing part of the story. We're missing the phase. And the phase, of course, is the delay that it takes the charge to actually travel from wherever it's stored to wherever you need it. And so the way the ICs really work here, if we think in time domain where we can combine magnitude and phase together, the IC is going to draw some charge. In this case here, I'm representing it just as a simple triangle wave, and that's pretty close to accurate. It depends, of course, exactly on what's going on in the IC, but overall, it's most of the time-varying current that the IC needs is somewhat triangular in shape. And so we're going to charge up a pair of parallel planes, a power and a ground plane pair, with some battery here and through some very large inductance. And we can calculate what the total charge is going to be here, and then we can add an IC. We can move that IC, we can move the capacitor, rather, add a capacitor and move that around to see how that changes the overall voltage here at the port 2, where we're actually drawing the charge from. So the port 2 would be the IC power pin, where it's drawing current from the power ground plane pair and the decoupling capacitor eventually, and we'll see what how the voltage varies there. So first of all, we can calculate what the total charge is on the between the power ground plane pair, just based on the size. I can come up with a capacitance of 3.5 nanofarads. If we use the 3.3 volt DC supply, then we end up with 11 nanocoulombs. And the pulses I was showing you a moment ago, if I have a 5 amp peak and a 1 nanosecond base, I can calculate the charge under there as 2.5 nanocoulombs. So what this means is that if I don't have any capacitor or any way to replenish the charge between the two parallel plates, that after a little more than 4 cycles, I'll have depleted the charge completely, and the voltage will be down to 0. Of course, if I don't replenish the charge, I start out at 3.3 volts, 11 nanocoulombs. First time I draw 2.5 nanocoulombs out of there, I drop down to 8.5 nanocoulombs. The capacitance hasn't changed, and so the only thing else that can change is the voltage. And so I'll lower the voltage, and I keep lowering the voltage each time I draw a charge until I end up with nothing. So this is just a bigger picture of the charge that I'm drawing. And now what we see here, we're looking at the voltage as the function of time, the voltage at the IC pin, and you can see here represented is the triangular draw of the IC, and it happens right when you see this dip in voltage. And if I have no capacitor on there, as I mentioned, I would draw by 2.5 nanocoulombs, and I'd drop in voltage down to about 2.6 volts. Next time I draw again, I'm down here a little less than 2 volts, and eventually I would be down to 0 volts. If I put a capacitor there, say at 5 inches away on the circuit board, you can see that my voltage is still dropping, and then eventually it starts to build up again as the charge from that capacitor finally reaches the IC pins. And it's probably no big surprise that if I put the capacitor very close to the IC, I'll say only 50 mils away, while the voltage dips down, it doesn't dip as far because the capacitor can start providing that charge sooner, and I come back up before I finally draw some more charge, and so the overall droop is less, as well as the size of the ripple. If I have inductance associated with a capacitor, if I set the capacitor at 400 mils, just under a ½ inch, and change the connection inductance here, it's probably no big surprise that with the biggest amount of inductance, it's the more difficult for the capacitor to provide charge, and so it takes longer for that charge to come in, so the droop is greater. If I have less connection inductance, probably ½ nanohenry is about as good as we could possibly get, then the droop is not as deep, and the recovery time is faster because the charge can get there faster. All right, so we know now that by looking at this, that we can see how the voltage changes as current is drawn, and now let's see what happens as we change the number of capacitors we have. So I'm going to take a case here. Here's my power pin, like I had before, and I'm going to put a decoupling capacitor, and I'm going to move it around as well, but that's not important. But I'm starting out with one capacitor at 1 microfarad, and then I'm going to go with 2 capacitors here at ½ microfarad each, so still a total of 1 microfarad. And ultimately, I'm going to go with 4 capacitors at a ¼ microfarad each, so again, a total of 1 microfarad. And so if the value of the capacitance is what's important, I would see no difference between these 3 different cases, right? Because the capacitance, the total capacitance, is staying the same. But what we see is it really does make a difference, looking at the same kind of thing. What we see here is that at some distance here, in this case here I'm at 800 mils, we can see that if I had 4 capacitors, I don't go down as far, and I start recovering it faster than I do if I had only 1 capacitor and the same amount of capacitance. You see the droop is greater and the recovery time takes longer. And basically, the way I like to think about the a capacitor is nothing more than a bucket of electrons. And so how many electrons can I have in my bucket is dependent on the amount of capacitance. Remember, the formula I showed you before related to voltage, the charge, which is the number of capacitors, and the capacitance, right? And so all these things go together, and if I have more capacitance, I have more charge for given voltage. So I get a bigger bucket. If I have a bigger bucket, I'm going to be taking electrons out. You can think about dipping your hand into a bucket and taking the electrons out. And the speed at which I take the electrons out is associated with the inductance. The more inductance, the slower I can take the electrons out. Well, if I go along with this analogy, and now I have two buckets, and I use both hands taking electrons out, one out of each bucket, you can see that I'm going to get more electrons out over a unit of time because I have these two inductances in parallel, if you will. I've got two hands working. And while I don't have four hands, you can imagine that if we had a friend working with us in four buckets, and at the same speed, we can still get more electrons out. And so the voltage dips less. So the value of the capacitor is not important as long as you have enough capacitance. Okay, that is, as long as I don't run out of charge. Then it doesn't matter how many electrons are in the bucket. I'll take out what I need for now, and the bucket will get refilled by the power supply later on. If I look at longer time record, you can see that this dipping goes down, and eventually I reach an equilibrium where I'm have this ripple here. But again, the droop is much greater when I have only one decoupling capacitor of 1 microfarad than when I had 4 decoupling capacitors, still totaling 1 microfarad, because again, I have those inductances effectively in parallel. So I just need enough charge to supply the need, and the effect of the capacitor value is not that important. So here's another example to show the same sort of thing. Here I've got this purple line has 1 decoupling capacitor at 0.8 microfarads, and then the blue dotted line has 1 decoupling capacitor at 8 microfarads. So 0.8 and 8 are a factor of 10, right? If the value of the capacitance was important, I would expect to see some change here. But indeed, we don't. We see the purple and the dotted blue line is exactly the same. Now, if I was to look at, say, 1 capacitor at 8 microfarads, the blue line, dotted line, and 8 capacitors at 1 microfarad each, so still a total of 8 microfarads. So the blue here and the red here are the same amount of capacitance. The difference is 1 or 8 capacitors, and you can quickly see that there's a big difference. And having 8 capacitors is much better than having 1 capacitor of the same total capacitance. Again, as long as there's enough charge. And enough just means that my capacitor has to be large enough so that I don't run out of charge during the time I'm doing this. All right, so if I was to put 2 decoupling capacitors right next to each other, is that as good as having 2 capacitors placed far away from each other? In the previous example, I had a ring of 8 capacitors, so they were as far apart as possible in a ring around the IC. And that's not often how we do our boards. Oftentimes we'll put our capacitors all along one side. And so I wanted to see what would happen. Now, if I was to put 2 capacitors right next to each other, in this case here I'm going to use a perfect capacitor, which is the via between the planes, to see what the inductance is at this observation point. If I put 2 right next to each other, I could kind of imagine the current coming out of 1 capacitor flowing downward towards the observation point, which is my IC power pin, and another capacitor right next to it, and that current flowing down to it. And so I got 2 current loops here, and there's a lot of mutual inductance between them, and that's going to increase the amount of impedance. So I could kind of imagine that if I was to move that capacitor far away, maybe down here at the bottom, the second capacitor at the bottom, the first one at the top, now the loops of current are in the opposite direction, and the mutual inductances will cancel. And then I wonder, well, as I move around on this arc, as I move around on this arc, what happens? So if it is 90 degrees just as good as 180 degrees and so forth. So that's the experiment we wanted to do. And actually, we ended up with a formula that's relatively straightforward here that was developed at the University of Missouri Science and Technology. And you can see here, all it is some simple dimensions are the distances here and so forth. And that can calculate that inductance that the port 1 would see for some distance r as we go around the circle. And the bottom line is curves like this. Now, the x-axis is the angle around, so 180 degrees, where the second via or perfect capacitor would be at the bottom, is out here. And then we see the inductance. And we can pick any one of these distances here. Let's pick, say, the closest one, 250 mils. We start, if we only had one via, one perfect capacitor, we start with about 1150 picohenries. And then we can see as we go around that circle, we decrease, but then it kind of flattens out. By the time we get here to 90 degrees, it's kind of flat, and certainly by the time we get to 180, it's flattened out. But at 180 degrees, we're at 800, which is not half of 1150. And so what we're seeing here is that while we get an improvement by moving capacitors away from each other, we never get to that factor 2 that we would expect by having a second capacitor. And that's the same for different distances. Here I've got plane separation of 10 mils. The previous example was 35 mils, and so forth. And it really doesn't matter what the distance is. The curves are going to be the same, just the exact numbers are changing. And if instead of moving around in an arc, we just keep them straight, then you can see we can adjust that previous formula so that the distance of the second capacitor gets longer as it gets further away. And we get the same sort of effect. Instead of getting down to about 75% of what it was before, it only gets down to maybe about 80% or so. It doesn't go down as far, and that's because the second capacitor is moving further away. All right, so let's understand this a little bit better. Why are we not getting to the point of the factor 2 that we might expect? And so we actually created a board here. And we did some simulations to look at current density as well as some measurements, and you'll see those in a minute. But basically the bottom line is we got this large board, and the thing we're looking at is right here in the center, so we're not going to get any effects of the edges and so forth. And we ended up with our observation point here, and one via, up at the top, 2 vias with a separation of 30 degrees, 90 degrees, or 180 degrees. And what we get finally for a result here is these current densities. And what we see is if I only had one of the vias, then in the middle here I can see that I got a lot of oranges and dark mustard colors. And that means the current density is fairly high in the middle. And if we look at the formulas for inductance, what we find is that loop area is the most important thing. And that's certainly true, and that's what anybody who knows inductance will tell you, that the loop area is the main thing that affects the value of the inductance that we have. However, the current density is also important. It's a secondary impact, but it's still important. And so here we see the current density is pretty high in the middle, and so the inductance in this case is going to be the highest case. And that's what we saw in the previous charts. If I come to a case where they're 30 degrees separated, we start to see, instead of the really dark colors, we're seeing some yellows now. Still got some of the dark mustard, but not as much. And then at 90 degrees, we're seeing greens. So it's even lower current density here in the chart. And at 180 degrees, we're still seeing the greens. So this is kind of, if you remember a couple of charts ago, the difference between 90 degrees and 180 degrees was very minimal, and that's because the current density is about the same in both cases. All right, but if we also look at this, we can see that around the IC pin, we have this dark red because the current is coming down in all directions, trying to come in, right? And that remains true no matter what we have here in close to the IC. In this case, we only had one power pin, and the current stays very highly dense. And so while the current density is lower out here in the middle away from the pins and the capacitors, right in close, it's still very high. And so that answers why we actually didn't get down to that 50% point, because while a lot of the path, the current density was was lowered. Not all of the path was a current density lowered. And right in close, it didn't go down. And we actually have some measurements where we actually built a board and have some shorting vias on it and measured what the impedance was with a network analyzer, and we ended up with curves that look like this upper chart here, and we can just extract the inductance off this rising curve, plot it along with what that formula was, and you can see that the measurements validated the simulation, or that formula, I should say, very well. So this formula is a good formula that you can put into a spreadsheet and just kind of check for yourself your designs. So let's start thinking now about what happens when we have multiple capacitors. And we might have them in different configurations. The next chart I have actually has data from the case where we had the pads separated only by 40 mils. If we had to go with surface mount capacitors here, 0603, 0402, you can see that the inductance would actually increase. So the curves are actually set up for this 40 mil spacing. The curves you're going to see in the next chart. We'd have to increase the numbers if we wanted to do this for 0402, 0603, 0805, and so forth. But the question comes down to, what is the configuration we're going to use? Now, if I take 16 capacitors in this example, I can put them all in a row like I've shown here in the dense non-alternating upper left-hand side. Although I might decide to alternate the power and ground pins here like I did in the upper right, so I'm alternating them here. Or I might spread them out, similar to what I did a few slides ago, but not alternate the power and ground pins. Or I might spread them out and alternate them, and we'll see what happens from that. And so here is the inductance as I go deeper into the printed circuit board, okay, for the 40 mil spacing. And the dark blue curve here that we see at the top is the dense non-alternating case, going back here, the upper left-hand case. So this is what we normally do, right? Have all our capacitor power pins lined up, all our ground pins lined up. And what we see from this chart here is that this is the absolute worst thing you can do. So the thing that we always do is the worst possible thing to do. If we were just to alternate the pins and keep all the capacitors close together, we get this purple line. And you can see that when I'm up near, when I only go down a little distance into the printed circuit board, you know, one layer down or something, there's not a lot of change here. But as I go deeper and deeper and deeper, I diverge from the dark blue case dramatically. And that's because I'm getting a mutual inductance cancellation. If I go back here and we think about the power and ground pins here being alternating, basically the current is going in the opposite directions on the power pins and the ground pins as the IC draws the current. And so that opposite direction gives me a cancellation of the mutual inductance and lowers the overall effective inductance. And that's what we see here. So the deeper I go, the more I get the canceling effect. Now, if I spread out my capacitors, I use the red and green lines down here, and you can see that if I spread them out, especially if I'm only going down a few layers, that improves things. It's not awfully huge, but it still improves things. And it really doesn't matter too much if I'm spread out, whether they're alternating or not alternating, because the spreading itself is making sure that I'm getting a lower current density, and they're spread out so much that there's no real cancellation of the mutual inductances because they're too far away. So you can see here again that the worst thing you can do, if you take nothing else away from the seminar, we should not be doing our capacitors in a line with the power and ground pins lined up nicely in a row like good soldiers. We should be alternating them to reduce that effective inductance and make our capacitors more effective. Now, we can start looking for some convergence on this, and so here I've got another example where we're putting all our capacitors in a line, and I might have the regular type of configuration where everything's lined up, or the alternating one. And what I wanted to point out here is that, remember that when we added a second capacitor a few slides ago, we did not get a reduction of inductance by a factor of 2. And I explained why that was, and so forth, but that'd be expecting a 1 over n, right? If I double the number of capacitors, I would expect my inductance to go down by a factor of 1 over 2. So here I'm plotting this 1 over n, in this particular case, for 5 mils between the planes. The height here is 5 mils. If I have the regular type configuration where all the power and grounds are lined up, you can see the inductance goes down as I add more capacitors, but not as fast as 1 over n. However, if I alternate them, I get the dotted blue line, I actually lower this effective inductance by much faster than 1 over n. And so we can kind of look at this curve over here on the left, which is the same data except on a linear scale. And what we see basically is the point where the number of capacitors really is not lowering the effective inductance is reached much faster when we have the alternating than when we have the regular lineup. And this just shows for another size, but actually I'm going to make one more point here, and that is if I wanted to, let's say I decided that in order to have a good decoupling capacitor design, I needed to have my inductance, my effective inductance, no more than 0.025 nanohenries. So that's right here. I can kind of draw an imaginary line across here. And so you can see that I can reach that amount of effective inductance with about 4 or 5 capacitors if I alternate them. But if I don't alternate them, I have to come out here to something like 14 or 15 capacitors before I get the same effective inductance. So if nothing else, using this alternating approach can allow me to use fewer capacitors. And that's really good for dense high-speed boards because, first of all, capacitors cost money, not an awful lot of money, but they take up space on the board, which is valuable, and they have vias that usually go all the way through the board, which takes up wiring channels inside the inner layers, even if they're not being used. So reducing the number of capacitors can reduce the pressure on the amount of wiring channels and potentially even reduce the number of layers you might need on your board because you open up more wiring channels. So all this is a very positive reason for using this alternating approach. Now we can actually make it even better a little bit. Here's the regular again and the alternating, same line configuration, same number of capacitors in the effective here. But let's suppose we were to put the capacitors in this pair like this. So now I've got 2 capacitors and I'm alternating the power and ground pins, and I'm bringing them off to the sides rather than off the ends here. And you can see that whether I line these pairs up in a horizontal or in a line like this, it really doesn't matter because from pair to pair, the mutual inductance is low, and so it doesn't have an impact to how we line them up. But you can see both the purple dotted and the green line here is even better than just the alternating approach that I was talking about a moment ago. So using this pair of capacitors set up like this, and then lining them up so that the power and ground pins are alternating, you can lower the inductance even more and even more reduce the total number of capacitors that you need on the board. And so here again is the same chart except in a linear fashion, and here I put a dotted line across here to show that if I wanted 0.01 nanohenries in this example, if I go with the traditional way of doing things, I'm going to need more than 30 capacitors. If I just alternate the capacitors, as on the upper left here, I'm down somewhere around 8 or 9 capacitors, and I could probably reduce it down by 1 or 2 capacitors even more by going to this kind of configuration. So this can have a big impact on the number of capacitors that you have to put on your board and still have it function properly. So overall, we can see that adding additional capacitors doesn't lower the effective inductance to 50%. It only lowered it down to about 70 to 75%. Of course, as we had thicker dielectrics, we would expect higher inductance between the planes, but the alternating of the power and ground pins can significantly reduce the overall inductance dramatically. Now let's also talk about narrowing the planes. I've seen this before in cases where people will have this odd shapes because you have many power layers or power islands on a certain layer, and in order to get from where the regulator is to where the IC is, we might have this kind of weird shape that has a relatively narrow plane. So I took a case here where I had a 12-inch wide board and separated them, the two ports, by 10 inches. And then I also have a 10-inch wide. I'm going to cut this down to 5 inches wide and 2 inches wide. And I'm going to look at what the inductance is at port 1 when I short port 2 together. So I've got a power ground plane pair with one via shorting them together here at port 2. And I just want to see what the inductance is at port 1. So you can see that you can think that the IC would be at port 1 and my decoupling capacitors would be at port 2, okay, as I go with narrower planes. And so here's a side view. Here you can see the two planes, the shorting via, which is my perfect capacitor, 10 inches between them, and so forth. And the results that we get, if the plane is very wide, 10 inches wide, I get about a half a nanohenry of inductance. However, as I narrow that plane down, you can see that I go very quickly over 1 nanohenry to even 2.5 nanohenries by having only a plane width of 1 inch. But going back here, the distance between the planes is only 10 mils, and so it would seem that narrowing the width here would not have that big of an impact. But you can see the amount of inductance is increased dramatically, and that's because the current density is gone up. The current is constrained to stay within only, in this, say, 2-inch case, within 2 inches, where in the case of a 10-inch wide board, the current can spread out. And so the current tries to spread out to minimize the overall inductance, as well as tries to stay tightly coupled to minimize the loop area. So there's two things going on. Loop area, again, is the most important thing, but the spreading out to minimize the current density is also important. If I was to reduce the distance between the vias, say down to 2 inches here, this first column of distance of 10 inches is the same as the previous chart. Here, though, in the middle column, I've got 2 inches. You can see that the difference in the inductance as I go from 10 inches to 5 inches wide is almost nothing. It isn't until I get down to 2 inches that it starts growing, and 1 inch grows even more. If I only have 1 inch between the shorting via, the perfect capacitor, and the IC power pin, you can see there that going from 10 inches down to 2 inches has almost no impact. It isn't until I get very narrow down to 1 inch that I start to see some impact. And so basically the bottom line is, if I have to go a long distance between my decoupling capacitors and my IC, I need to make sure the planes are wide so that current spread can occur. If I don't need to go very far, then I can make the planes much narrower and be okay. But still, even when I make them narrow, only going an inch here, you can see that when the plane width became an inch, I increased the amount of inductance. So really the plane width should be greater than the length of the run to keep that inductance as low as possible. And this kind of gives an example of the current density. If I have a wide plane here, you can see that the currents are spreading out, kind of greens way out here at the edges. But in the narrower ones, I've still got some oranges, and I don't ever get down to a current density of the green. And so the current density stays higher, meaning the inductance will stay higher because the current is constrained. All right, so now I wanted to show a case study here. All this has been nice with nice simple geometries. Let's go back and look at a more real-world case here. And so I got a 44-layer board that I use as an example here, and my power ground plane pairs that I'm using are in the middle. I've got some distance out to some capacitors. I've got a bunch of power and ground pins here in the middle of the IC region. And we want to see what happens as we change different things. So I've got a matrix here of 9 different cases we're going to look at. Across the top, I'm changing where the power planes are. The power planes in the middle, the power planes at the top layer, or the power planes way down at the bottom layer. The y-axis here, I'm changing where the decoupling capacitors are located. So in the upper row, I'm putting the decoupling capacitors only at the top, as you can see here. In the middle row, I'm putting the decoupling capacitors only at the bottom, and off at some distance away, 300 mils I think it was. And then the bottom row here, I'm just putting the decoupling capacitors directly underneath the IC. I've had a lot of people tell me, oh, always put the decoupling capacitors directly under the IC because that always lowers the inductance and therefore the impedance. Let's see what happens. So first we're going to look at the power layer location. Remember, I had it either at the top of the stack up, in the middle of the stack up, or the bottom of the stack up. And what we see here is that these two regions, of course, the total capacitance hasn't changed. Total capacitance hasn't changed, and so this lower part of the curve is not changing at all. In the middle region, where I had the LIC and the L planes and all that, we can see that putting the power plane at the top gives me the lowest amount of inductance, the lowest impedance. And up here at high frequencies, where I said it was only the distance between the IC pins and the power planes was going to be involved, well, you can see it makes a difference, and indeed it does here. And again, when the power planes are near the top, of course, the distance we have to go down the V is minimal, and so the inductance and therefore the impedance is minimized. If I put the capacitors, this left-hand case was with the capacitors on top. If I put the capacitors underneath the IC, then we still see here at the upper frequencies, it doesn't matter because it's only about the distance the IC has to go down through its vias to the power layers. But I am able to make some improvement in the middle region here, where basically it doesn't matter whether we put the power planes at the top, middle, or bottom. Because the capacitors are on the bottom, they're dominating the impedance of this middle section. All right, so that's moving the power layer. Now let's look at moving the capacitors. If we have the power at the top, the left-hand case here, and now I'm going to put the capacitors either in the top, on the bottom, or the bottom right underneath the IC. Well, the first thing we notice here is that it doesn't matter. It's high frequencies. There is no change at all at these high frequencies because this high frequencies, again, are only affected by the distance from the IC pins down to the power layers. So it doesn't matter where I put the capacitors. But over here in the middle region, we can see that if I put the capacitors on top, I have the lowest amount of inductance and therefore impedance. And if I put the capacitors on the bottom at some distance away, that's actually the worst case here. And if I put the capacitors right underneath the IC, that's in between the two cases. But in this case, when the power is at the top, when the power planes are at the top of the IC stack-up, I mean the printed circuit board stack-up, it's much better to put the capacitors on the top around the IC than it is to put them directly underneath the IC. Now, if I come over to the right-hand case here, where my power layers are in the middle, again, it doesn't matter whether I put the capacitors at the high frequencies. Now, what we see is if I put the capacitors on the top or the bottom away from the IC, it doesn't really matter here. The blue line is and the red line are right on top of each other. If I put the capacitors directly underneath the IC, it makes a little bit of improvement, but not a whole heck of a lot. And so in this case here, putting the capacitors right underneath the IC makes a little bit of an improvement, but not very significant, probably not worth the trouble it was to put them there to begin with. And again, at very high frequencies, it doesn't make any change at all. So now let's look to see what happens as we have different number of ground planes. And so the upper left case here, all ground planes mean that if you remember the stack-up had a lot of different ground planes in it here, even though the power layer only had one power layer here in the middle. If I keep only the top and the nearby ground plane, so I'm going to keep the ground plane on the top here, and the nearest ground plane, we're going to look at see what the inductance is, but the intermediate grounds are removed. If I keep only the bottom ground plane, the nearby bottom ground plane, so now my power layer is right here, and the ground layer is here. It's actually further away than the upper right-hand case, but it's the nearest one below it. And then finally keeping only the top and bottommost ground planes, so there is no ground plane near the power plant at all here, but we've got grounds at the top and the bottom, and let's look to see what happens. And so what we see here is, first of all, only having the topmost and bottommost ground planes was the worst case. The distance, the loop area is much greater, and so the inductance is greater and the impedance is greater. In this mid-range region here, really having the, as long as we had a nearby ground plane, having all the other ground planes didn't really matter anymore. And so whether they're there or not really is not affecting, because the inductance between the planes is all about just what's happening between the planes. And then finally, at the higher frequencies, we can see that having all the ground planes makes things a little bit better. Certainly the top and the closest is about the same. Having only the bottom closest is not quite as good, because the distance between the planes, power plane and the ground plane, was a little greater. But overall, it really didn't make a whole heck of a lot of difference, as long as we had a nearby ground plane to the power plane. So overall, I think that the cause of the inductance, we can go back to the fundamental physics and see what the physical cause of the inductance is, and we can break that overall current path into pieces of the vias from the IC, the planes themselves, and the distance out to the decoupling capacitors, and then the effect of the decoupling capacitor via connection as well. The value of the capacitance is not as important as the number of capacitors. In general, having more capacitors is better. And the value of the capacitance is not important, and so why not just use as large a value of capacitance as possible? Because after all, if there's nothing more than a bucket of electrons, I want my bucket to be as large as possible, as long as it doesn't slow me down taking the charge out. So if I have a bigger bucket, but I can still get the electrons out just as fast, then that's ideal. So that means once you've picked your surface mount capacitor size, 0402, 0603, 0805, whatever it is, you might as well go for the largest value of capacitance. Actually, I'm told that the largest value of capacitance is got a poorer MTBF, mean time between failure, than all the other values. So you're actually better off, just from a reliability standpoint, to pick your package size and take the second largest value of capacitance as you can get in that package size. We saw that the via connection configuration for capacitors can dramatically influence the inductance. Just alternating the capacitors when we place them close together makes a huge impact, or if you just spread them out, it can improve the amount of the effective amount of inductance that we have. And I even showed you a pair, how we can go with a pair configuration to kind of optimize that. And then we also saw that if the power ground planes are deep in the printed circuit board stack up, where we put the capacitors has less impact than we might expect. However, if the power ground planes are high in the stack up near the top where the IC is, then putting the capacitors on the top can have a much better impact than putting them directly underneath the pins. It's all about the inductance of the overall current path. So I think some conclusions. We want the power ground plane pair to be close to the IC as possible. I think I've said that a couple times. We want the capacitors close to the power layer to minimize the inductance that the capacitor is going to see to recharge the power planes. We want the separation between the power ground plane pair to be small as possible, although usually that's not really something that's selectable. But the closer we get the power and ground planes together, the less inductive loop we have, because the loop area is smaller between the two planes. The ground plane that's closest to the power layers is going to affect the response the most, which kind of makes a lot of sense, I think, pretty intuitive. And all the other ground planes have very little impact on this particular effect. Of course, the other ground planes could be important for other reasons, like references for strip lines or returns for other power layers and so forth. But for the one that we're looking at, the closest ground plane is the most important one. And we want the ground vias to be placed as close to the terminal, the ground capacitor of the capacitor's ground terminal. We don't want to have a large amount of inductance there. So if we put the vias far away from the capacitor's pads, then that just increases the loop area. And so vias should always be as close as possible. Ideally, if we could put the vias right in the capacitor pad itself, that gives us the lowest amount of inductance. But oftentimes, for manufacturing reasons, we can't do that. We have to have them spaced some ways apart, and we want to minimize that. So that ends my presentation, and I'd be more than happy to answer any questions that might come up.
Well, thank you, Bruce. I did get a question in. Does parallel vias have any influence?
Yes, if we could have two vias for the power pin of a capacitor, for example, and two vias for the ground pin, then that lowers the amount of current density in the via and lowers the overall inductance. So that can have an impact. It would have a positive impact. In fact, it would lower the inductance. However, the alternating approach that I showed is much better. Although I guess if you were to alternate with two vias, that's probably even better. Although I have to admit I haven't tried that configuration.
Well, that brings up the other question that I have here. Referring back to your slides 29 and 30, I'm hearing a question to go over the alternating placement again as far as how the physical layout is done. Okay, so the upper right-hand configuration here, upper left-hand configuration, sorry, is how we would normally do it. Say all the green boxes are the ground pins, and all the maroon ones or mustard-colored ones are the power pins, and the same here. Versus alternating them like this, so that I would have a power. This would be my capacitor here, and then the next capacitor next to it would have the power and ground swapped. And the next capacitor next to it would go back to the original and so forth. So we're alternating the power pins and the ground pins for the capacitors. And then if we look at the results, again, the dark blue line is the case where we line them all up so all the power pins on the capacitors face the same direction right next to each other, and that's the worst case. And so again, like I said earlier, what we normally do is the absolute worst case. We can reduce the number of capacitors we need just by alternating them, because the overall effective inductance goes down, and therefore the impedance goes down. They're not sure which slide it was, but on one of your early slides, it looked as if the chip was at one location and the group of decoupling capacitors another. Was this not like placing capacitors near the IC? I think it's that. Okay, so here's the IC, and you can see we had some decoupling capacitors that were relatively local here, pretty close. You see the outline of the IC here, so that we couldn't get any closer than that. And then we had some bulk decoupling capacitors way out here, and then the voltage regulator way down here. This is actually a real design that we took this example from. Okay. Those are the questions that I've received. If anyone has additional questions, we'll be looking for input. And I don't see any more coming in. I want to thank Bruce for this excellent presentation. And I want to go over a couple of items here as a closeout. We have 3 more webinars in this 6-pack series that's being going on right now, the April 30th, June 3rd, and June 24th. And we look forward to seeing people attending those as the time goes on. And Bruce, I understood that you have some upcoming items near the Boston area, or any other activities that would you like to discuss with us, share with us? Sure. I'll be teaching in the first week of June in the Boston area, a 3-day seminar on printed circuit board design for EMI control. And you can go to my website, www.brucearch.com,
and you can see links to that seminar. And I'm also going to be teaching in October in the Boston area again a advanced EMC design seminar where I talk about a lot of different advanced topics such as lossy materials, electromagnetic band gap filters, and things like that, as well as simulation techniques and which modeling tools and techniques can be effective for what kinds of EMC problems to help understand the fundamental physics.
Oh, good, good.
And that's also on my website.
Well, okay, very good. Appreciate that. We'll pass that on to our things. We here at Washington Laboratories and the Academy Series have a lot of activities going on for webinars and resident courses on a lot of topics, including this Bruce six-pack series. We also have some wireless device approval, radio approval work that's distributed throughout this calendar year. A 461, Mill Standard 461 testing series things. It's 12 things offered every month this year. And if you've missed an item, any of these topics, the webinars are available as through this multi-part series, and you can mix and match them. In addition, if you see a topic that's already passed that you would like to be aware of, the recording is available. Please contact us to do that. Again, thank you very much, Bruce, for your excellent presentation, and look forward to working with you on the upcoming events.
Thanks,
and I'm going to check one more time for additional questions. No additional questions came in. Thank you very much, and with that, I will go ahead and close this event. Thanks again,
okay.
Bruce.
Bye now.